The video opens with a view of Earth, setting the stage for exploring the possibility of life beyond our planet. Juxtaposed with Earth is an artist's rendering of Kepler 1649, a potentially habitable exoplanet. The scene raises the fundamental question of whether Earth is the only planet capable of supporting life. Kepler 1649c is an exoplanet. Kepler 1649 resides approximately 300 light-years away from Earth. Kepler 1649 is located within the constellation Cygnus. Kepler 1649 orbits a red dwarf star. Red dwarf stars are smaller and cooler than our Sun. Red dwarf stars can exist stably for billions of years. Kepler 1649 is located within its star's habitable zone. The habitable zone is the orbital region around a star where a planet's surface temperature allows for liquid water. The presence of liquid water is a key factor in determining a planet's potential habitability. Kepler 1649 exhibits a high degree of similarity to Earth compared to numerous other exoplanets. The exoplanet Kepler 1649 is notable for its Earth-like characteristics. Thousands of exoplanets have been discovered, yet Kepler 1649 remains a standout. Kepler 1649 exhibits light levels comparable to Earth. The surface temperature on Kepler 1649 is similar to Earth's. Kepler 1649 possesses a gravity level comparable to Earth's, enhancing its potential habitability. The Kepler 1649 system shares structural similarities with our solar system. Both systems contain multiple rocky planets orbiting their respective stars. An asteroid belt-like structure is present in the Kepler 1649 system, similar to our solar system. Kepler 1649 is considered a promising candidate for potentially hosting life. Scientists have not yet detected life on Kepler 1649. The planet's characteristics make it a subject of intense scientific interest. Advanced telescopes, such as the James Webb Space Telescope, are deployed to analyze exoplanet atmospheres. The James Webb Space Telescope is used to study Kepler 1649's atmosphere. The telescope searches for biosignatures within the atmospheres of distant exoplanets. Scientists are actively searching for biosignatures in the atmospheres of distant planets. Biosignatures include life-supporting gases and potential artificial signals. The search for biosignatures aims to determine the potential habitability and existence of life on other planets. Kepler 1649 is theorized as a potential candidate for hosting life, raising the possibility of an extraterrestrial civilization. Hypothetically, inhabitants of Kepler 1649 could observe Earth as a distant blue dot in their night sky. The existence of a civilization on Kepler 1649c opens up possibilities for comparative planetology and astrobiological research. The possibility of humanity traveling to Kepler 1649 is explored. Kepler 1649 is located 300 light-years away from Earth. Interstellar travel to such distant exoplanets presents significant challenges. Reaching Kepler 1649c raises ethical questions about space exploration. Ethical considerations include the nature of first contact with potential life forms. Resource exploitation on Kepler 1649 introduces further ethical dilemmas. The discovery of an Earth, too, raises profound questions about humanity's responsibility as a species. Interacting with a potentially inhabited world necessitates careful consideration of the choices we would make. Humanity must contemplate the ethical implications of contacting and potentially influencing a new civilization. The video concludes by reiterating the question of whether Earth is alone in the universe. Viewers are encouraged to share their thoughts and perspectives on the possibility of extraterrestrial life. The search for life beyond Earth remains one of humanity's greatest scientific and philosophical endeavors. Kepler 1649 orbits a red dwarf star, completing its revolution in a relatively short period. Red dwarf stars emit significantly less energy compared to our Sun, influencing the conditions on orbiting planets. The orbital characteristics of Kepler 1649 are crucial for understanding its potential habitability despite the low energy output of its star. Earth and Kepler 1649 are compared to illustrate their size similarities. The side-by-side comparison emphasizes the comparable dimensions of the two planets. Visual analysis reveals the close size relationship between Earth and Kepler 1649. Kepler 1649's distance from its star allows for potential liquid water on its surface. Atmospheric conditions play a crucial role in maintaining liquid water on Kepler 1649. Simulation models predict the possibility of stable liquid water regions on the exoplanet's surface. Spectroscopy is used to analyze exoplanet atmospheres and identify their chemical composition, The absorption spectrum reveals the elements present in the exoplanet's atmosphere. Analyzing light from distant worlds helps scientists understand their atmospheric properties. The search for artificial signals involves using radio telescopes to scan the cosmos. Signal processing techniques are employed to identify potential artificial signals from extraterrestrial civilizations. Detecting artificial signals requires distinguishing them from natural astronomical phenomena. Contact with an alien civilization presents potential ethical dilemmas. Risks associated with alien contact include unforeseen consequences for humanity. Rewards of alien contact may include scientific advancements and expanded understanding of the universe. Interstellar travel faces significant challenges due to the vast distances between stars. Current propulsion technology imposes limitations on achieving interstellar travel within a human lifespan. The energy requirements for accelerating a spacecraft to interstellar velocities are immense. Terraforming Kepler-1649 presents significant technological and environmental challenges. Atmospheric modification is crucial for making Kepler-1649 habitable for humans. Regulating planetary temperature is another major hurdle in terraforming Kepler-1649. This simulation visualizes a potential biosphere on Kepler-1649. Hypothetical plant life is shown adapted to Kepler-1649's unique environment. The simulation also includes hypothetical animal life adapted to the planet's conditions. Panspermia theory proposes that life can spread throughout the universe. Asteroids and comets may act as vehicles for transporting microorganisms between celestial bodies. Kepler-1649 is a potential candidate for receiving life via panspermia. Kepler-1649's gravitational effects influence its host star, causing a subtle wobble in the star's orbit. The gravitational interactions between Kepler-1649 and other planets in the system create complex orbital resonances. These gravitational effects demonstrate the intricate dynamics of exoplanetary systems. The radiation environment around Kepler-1649 is analyzed to determine its habitability. Stellar flares from Kepler-1649 can significantly impact the radiation levels on Kepler-1649. Cosmic rays are also considered as a factor influencing the radiation environment of Kepler-1649. Kepler-1649 may exhibit geological activity, including volcanic formations. The possibility of plate tectonics on Kepler-1649 is under consideration. Geological processes on Kepler-1649 could include various forms of seismic and surface activity. The chemical composition of Kepler-1649's crust is speculated upon. The chemical composition of Kepler-1649's mantle is speculated upon. Models of planet formation and the composition of its star inform these speculations. The presence of a magnetic field is crucial for a planet's ability to deflect harmful solar radiation. Kepler-1649's potential magnetic field is a key factor in determining its habitability. Without a magnetic field, a planet's atmosphere can be stripped away by solar wind, rendering it uninhabitable. Tidal locking occurs when a celestial body's orbital period matches its rotational period. In tidally locked systems, one side of a planet perpetually faces its star, while the opposite side remains in permanent darkness. Kepler-1649 is a potential example of a planet that may be tidally locked to its red dwarf star. Atmospheric circulation on Kepler-1649 is influenced by its rotation. Temperature gradients drive atmospheric circulation patterns on Kepler-1649. Cloud cover significantly affects atmospheric circulation on Kepler-1649. Cloud formation on Kepler-1649 involves the condensation of water vapor. Atmospheric gases, in addition to water vapor, contribute to cloud formation processes. Condensation leads to the formation of clouds in Kepler-1649's atmosphere. Precipitation patterns on Kepler-1649 are simulated to understand its climate. Topography influences precipitation distribution on Kepler-1649. Atmospheric circulation models help predict potential precipitation zones. Kepler-1649 surface features are visualized, presenting a hypothetical landscape. The visualization includes hypothetical mountains, valleys, oceans, and continents. These features are based on scientific estimations and artistic interpretations of available data. Kepler-1649's axial tilt influences the intensity of seasonal changes on the exoplanet. Orbital eccentricity contributes to seasonal variations by altering the planet's distance from its star. The combined effects of axial tilt and orbital eccentricity determine the overall seasonal climate patterns on Kepler-1649. Extremophiles are organisms that thrive in extreme environments. The existence of extremophiles on Kepler 1649 is a possibility. Kepler 1649's extreme conditions could potentially support unique forms of life. Kepler 1649 may possess subsurface oceans, indicating the presence of liquid water beneath its surface. The existence of subsurface oceans suggests potential conditions for liquid water to exist beyond Earth. Liquid water beneath the surface of Kepler 1649 could potentially harbor unique forms of life. Hydrothermal vents on Kepler 1649's ocean floor are hypothesized to exist. Hydrothermal vents could potentially support life in Kepler 1649's oceans, similar to Earth's oceans. Hydrothermal vents release chemical compounds that provide energy for chemosynthetic organisms. Chemosynthesis allows organisms to derive energy from chemical reactions independent of sunlight. Kepler 1649, a planet potentially lacking sufficient sunlight, could support chemosynthetic life forms. Unlike photosynthesis, chemosynthesis utilizes inorganic compounds as the primary energy source. Artificial intelligence can potentially aid in the search for extraterrestrial life. AI algorithms analyze vast datasets from Kepler 1649 to identify potential biosignatures. AI can identify patterns and anomalies in exoplanetary data that might indicate the presence of life. The Fermi paradox questions why extraterrestrial civilizations have not been detected despite the universe's vastness. The sheer size and age of the universe suggest numerous opportunities for life to arise and evolve. Various hypotheses attempt to explain the paradox, ranging from technological limitations to societal self-destruction. The Drake equation estimates the number of potentially detectable extraterrestrial civilizations in our galaxy. The Drake equation includes factors such as the rate of star formation and the fraction of stars with planets. Other factors in the Drake equation include the probability of life arising and the likelihood of developing detectable technology. The Search for Extraterrestrial Intelligence, SETI, project aims to detect radio signals from alien civilizations. SETI employs radio telescopes to scan the universe for artificial electromagnetic radiation. The project analyzes received signals to distinguish between natural phenomena and potential extraterrestrial communications. Interstellar communication faces significant challenges due to vast distances and signal degradation. Radio waves are a primary method for interstellar communication due to their ability to travel long distances. Electromagnetic radiation, including radio waves, offers a potential medium for transmitting information across interstellar space. First contact protocols outline procedures for initial interactions with extraterrestrial civilizations. These protocols emphasize caution, observation, and a structured approach to communication. The goal is to ensure mutual understanding and avoid misinterpretations during initial contact. Cultural exchange with an alien civilization presents both potential benefits and inherent challenges. Understanding alien communication methods is a primary challenge in cultural exchange. Potential benefits of cultural exchange include scientific advancements and new philosophical perspectives. Contact with an alien civilization could lead to significant technological advancements. Alien contact may accelerate progress in fields such as energy, medicine, and materials science. The exchange of knowledge could revolutionize current scientific understanding and engineering capabilities. Contact with an alien civilization presents potential existential risks to humanity. Conflict with a technologically superior alien civilization poses a significant threat. Exploitation by an alien civilization could lead to the depletion of Earth's resources and the subjugation of its inhabitants. The search for life beyond Earth represents humanity's enduring curiosity and ambition. Exploring the cosmos offers the potential to unlock new scientific discoveries and expand our understanding of the universe. The future of humanity is intertwined with our ability to explore, understand, and potentially inhabit other worlds.